The viscosity of a fluid is a measure of its resistance to gradual deformation by shear stress or tensile stress. For liquids, it corresponds to the informal concept of thickness. For example, honey has a much higher viscosity than water. Viscosity is a property arising from collisions between neighboring particles in a fluid that are moving at different velocities. When the fluid is forced through a tube, the particles which compose the fluid generally move more quickly near the tube's axis and more slowly near its walls. Therefore, some stress is needed to overcome the friction between particle layers to keep the fluid moving. For the same velocity pattern, the stress required is proportional to the fluid's viscosity. A fluid that has no resistance to shear stress is known as an ideal or inviscid fluid. Zero viscosity is observed only at very low temperatures in superfluids. Otherwise, all fluids have positive viscosity, and are technically said to be viscous or viscid. In common parlance, however, a liquid is said to be viscous if its viscosity is substantially greater than that of water, and may be described as mobile if the viscosity is noticeably less than water. A fluid with a relatively high viscosity, for example, pitch, may appear to be a solid. Etymology. The word viscosity is derived from the Latin viscum, meaning mistletoe, and also a viscous glue made from mistletoe berries. Definition. Dynamic viscosity. The dynamic viscosity of a fluid expresses its resistance to shearing flows, where adjacent layers move parallel to each other with different speeds. It can be defined through the idealized situation known as a couette flow, where a layer of fluid is trapped between two horizontal plates, one fixed and one moving horizontally at constant speed. This fluid has to be homogeneous in the layer and at different shear stresses. If the speed of the top plate is small enough, the fluid particles will move parallel to it, and their speed will vary linearly from 0 at the bottom to at the top. In particular, the fluid will apply on the top plate a force in the direction opposite to its motion, and an equal but opposite one to the bottom plate. An external force is therefore required in order to keep the top plate moving at constant speed. The magnitude of this force is found to be proportional to the speed and the area of each plate, and inversely proportional to their separation. The proportionality factor μ in this formula is the viscosity of the fluid. The ratio is called the rate of shear deformation or shear velocity, and is the derivative of the fluid speed in the direction perpendicular to the plates. Isaac Newton expressed the viscous forces by the differential equation where n is the local shear velocity. This formula assumes that the flow is moving along parallel lines and the axis, perpendicular to the flow, points in the direction of maximum shear velocity. This equation can be used where the velocity does not vary linearly with, such as in fluid flowing through a pipe. Use of the Greek letter μ for the dynamic stress viscosity is common among mechanical and chemical engineers, as well as physicists. However, the Greek letter eta is also used by chemists, physicists, and the IUPAC. Kinematic viscosity. The kinematic viscosity is the ratio of the dynamic viscosity μ to the density of the fluid ρ. It is usually denoted by the Greek letter nu. It is a convenient concept when analyzing the Reynolds number, which expresses the ratio of the inertial forces to the viscous forces, whereas a typical length scale in the system. Bulk viscosity. When a compressible fluid is compressed or expanded evenly, without shear, it may still exhibit a form of internal friction that resists its flow. These forces are related to the rate of compression or expansion by a factor sigma, called the volume viscosity, bulk viscosity or second viscosity. The bulk viscosity is important only when the fluid is being rapidly compressed or expanded, such as in sound and shock waves. Bulk viscosity explains the loss of energy in those waves, as described by Stokes' law of sound attenuation. Viscosity tensor. In general, the stresses within a flow can be attributed partly to the deformation of the material from some rest state, and partly to the rate of change of the deformation over time. In a fluid, by definition, the elastic stress includes only the hydrostatic pressure. In very general terms, the fluid's viscosity is the relation between the strain rate and the viscous stress. In the Newtonian fluid model, the relationship is by definition a linear map, described by a viscosity tensor that, multiplied by the strain rate tensor, gives the viscous stress tensor. The viscosity tensor has 9 independent degrees of freedom in general. For isotropic Newtonian fluids, these can be reduced to 2 independent parameters. The most usual decomposition yields the stress viscosity mu and the bulk viscosity sigma. Newtonian and non-Newtonian fluids. Newton's law of viscosity is a constitutive equation. It is not a fundamental law of nature but an approximation that holds in some materials and fails in others. A fluid that behaves according to Newton's law, with a viscosity mu that is independent of the stress, is said to be Newtonian. Gases, water, and many common liquids can be considered Newtonian in ordinary conditions and contexts. There are many non-Newtonian fluids that significantly deviate from that law in some way or other. For example, shear thickening liquids, whose viscosity increases with the rate of shear strain. Shear thinning liquids, whose viscosity decreases with the rate of shear strain. Thixotropic liquids, that become less viscous over time when shaken, agitated, or otherwise stressed. Rheopectic liquids, that become more viscous over time when shaken, agitated, or otherwise stressed. Bingham plastics that behave as a solid at low stresses but flow as a viscous fluid at high stresses. Shear thinning liquids are very commonly, but misleadingly, described as thixotropic. Even for a Newtonian fluid, the viscosity usually depends on its composition and temperature. For gases and other compressible fluids, it depends on temperature and varies very slowly with pressure. The viscosity of some fluids may depend on other factors. A magnetorheological fluid, for example, becomes thicker when subjected to a magnetic field, possibly to the point of behaving like a solid. Viscosity in solids. The viscous forces that arise during fluid flow must not be confused with the elastic forces that arise in a solid in response to shear, compression or extension stresses. While in the latter the stress is proportional to the amount of shear deformation. In a fluid it is proportional to the rate of deformation over time. However, many liquids will briefly react like elastic solids when subjected to sudden stress. Conversely, many solids will flow like liquids, albeit very slowly, even under arbitrarily small stress. Such materials are therefore best described as possessing both elasticity and viscosity, that is, being viscoelastic. Indeed, some authors have claimed that amorphous solids, such as glass and many polymers, are actually liquids with a very high viscosity. However, other authors dispute this hypothesis, claiming instead that there is some threshold for the stress below which most solids will not flow at all, and that alleged instances of glass flow in window panes of old buildings are due to the crude manufacturing process of older eras rather than to the viscosity of glass. Viscoelastic solids may exhibit both shear viscosity and bulk viscosity. The extensional viscosity is a linear combination of the shear and bulk viscosities that describes the reaction of a solid elastic material to elongation. It is widely used for characterizing polymers. In geology, earth materials that exhibit viscous deformation at least 3 orders of magnitude greater than their elastic deformation are sometimes called rheods. Viscosity measurement. Viscosity is measured with various types of viscometers and rheometers. A rheometer is used for those fluids that cannot be defined by a single value of viscosity and therefore require more parameters to be set and measured than is the case for a viscometer. Close temperature control of the fluid is essential to acquire accurate measurements, particularly in materials like lubricants, whose viscosity can double with a change of only 5 degrees Celsius. For some fluids, viscosity is a constant over a wide range of shear rates. The fluids without a constant viscosity cannot be described by a single number. Non-Newtonian fluids exhibit a variety of different correlations between shear stress and shear rate. One of the most common instruments for measuring kinematic viscosity is the glass capillary viscometer. In coating industries, viscosity may be measured with a cup in which the efflux time is measured. There are several sorts of cup, e.g., Zahn cup, Ford viscosity cup, with usage of each type varying mainly according to the industry. The efflux time can also be converted to kinematic viscosities through the conversion equations. Also used in coatings, a Stormer viscometer uses load-based rotation in order to determine viscosity. The viscosity is reported in Krebs units, which are unique to Stormer viscometers. Vibrating viscometers can also be used to measure viscosity. These models, such as the Dynatrol, use vibration rather than rotation to measure viscosity. Extensional viscosity can be measured with various rheometers that apply extensional stress. Volume viscosity can be measured with an acoustic rheometer. Apparent viscosity is a calculation derived from tests performed on drilling fluid used in oil or gas well development. These calculations and tests help engineers develop and maintain the properties of the drilling fluid to the specifications required. Units. Dynamic viscosity μ. Both the physical unit of dynamic viscosity and SI poisoy and the CGS units poise come from Jean-Léonard Marie Poisoy. The poisoy, which is never used, is equivalent to the Pascal second, or per square meter, or kilogram. If a fluid is placed between two plates with distance 1 meter, and one plate is pushed sideways with a shear stress of 1 Pascal, and it moves at x meter per second, then it has viscosity of 1 x Pascal second. For example, water at 20 degrees Celsius has a viscosity of 1.002 millipascals s, while a typical motor oil could have a viscosity of about 250 millipascals s. The units used in practice are either par s and its submultiples or the CGS poise referred to below, and its submultiples. The CGS physical unit for dynamic viscosity is the poise, is also named after Jean Poisoy. It is more commonly expressed, particularly in ASTM standards, as centipoise, since the latter is equal to the SI multiple millipascal seconds. For example, water at 20 degrees Celsius has a viscosity of 1.0020 millipascals s equals 1.0020 cp. 1 petaliter equals 1 pascal s. 1 p equals 0.1 pascals s equals 0.1 kilograms m-1 s-1 1 cp equals 1 millipascal s equals 0.001 pascals s equals 0.001 and sm-2 equals 0.001 kilograms m-1 s-1. Kinematic viscosity μ. The SI unit of kinematic viscosity is square meter per second. The CGS physical unit for kinematic viscosity is the Stokes, named after George Gabriel Stokes. It is sometimes expressed in terms of centistokes. In U.S. usage, stoke is sometimes used as the singular form. First equals 1 square centimeter s minus 1 equals 10 minus 4 square meters s minus 1. 1 cst equals 1 square millimeter s minus 1 equals 10 minus 6 square meters s minus 1. Water at 20 degrees Celsius has a kinematic viscosity of about 1 cst. The kinematic viscosity is sometimes referred to as diffusivity of momentum, because it is analogous to diffusivity of heat and diffusivity of mass. It is therefore used in dimensionless numbers which compare the ratio of the diffusivities. Fluidity. The reciprocal of viscosity is fluidity, usually symbolized by phi equals 1, mu or f equals 1, mu, depending on the convention used. Measured in reciprocal poise, sometimes called the RHE. Fluidity is seldom used in engineering practice. The concept of fluidity can be used to determine the viscosity of an ideal solution. For two components and the fluidity when A and B are mixed is, which is only slightly simpler than the equivalent equation in terms of viscosity, where chi A and chi B is the mole fraction of component A and B respectively, and mu A and mu B are the components' pure viscosities. Non-standard units. The rain is a British unit of dynamic viscosity. Viscosity index is a measure for the change of kinematic viscosity with temperature. It is used to characterize lubricating oil in the automotive industry. At one time the petroleum industry relied on measuring kinematic viscosity by means of the Seebolt viscometer, and expressing kinematic viscosity in units of Seebolt universal seconds. Other abbreviations such as SSU or SUV are sometimes used. Kinematic viscosity in centistoke can be converted from sus according to the arithmetic and the reference table provided in ASTM D 2161.